Okay, so we're going to start off with some general considerations, and hang in here with me. This is the most dense part of this class. When we move into psychopharmacology per se, it's going to take on much greater clinical relevance, and I think will be more palatable. And so I want to review then just a few things about the functioning of nerve cells, not just because I want you to know that in general, but we're going to look at the specific actions of drugs on nerve cells and see how their mechanism of action. And so, of course, there's a cell body with the dendrites, nucleus in here, axon, nerve impulse travels down the axon, and releases the neurotransmitter at the terminal end. It used to be thought that nerve cells only made and secreted one neurotransmitter. That's largely the case, but there are some exceptions. There are some nerve cells that can actually produce and release more than one neurotransmitter. But most of the nerve cells, they synthesize, they make the neurotransmitter in the nerve cell and secrete it, and then they get their name by the neurotransmitter that they release. So a norepinephrine nerve cell makes and secretes norepinephrine. Synaptic connections occur in probably 90% of the brain between the end of one nerve cell and a dendritic spine. Coming off of the dendrites, going back here for just a moment, the dendrites coming off of the cell body, coming on the surface of dendrites are a bazillion of these little spines. These spines are very dynamic and fluid. They can grow within minutes. They can retract within minutes. You can, the old saying, you can use it or lose it. If nerves are developed and synapses are used, and they tend to become more sturdy and steady. If they're not used, then spines will break apart from the synapse and shrink back down in. Nutrients to the neuron. The neurotransmitters are made inside the nerve cells, and they need the building blocks for this, okay? And this is supposed to be, I just drew this in, a little capillary here, butting up next to this nerve cell. And what diffuses across the nerve cell membrane are a number of things. Glucose, which is the only energy supply for the brain, okay? Oxygen, obviously, is absolutely necessary. But the building blocks for all these molecules that are made inside the nerve cell are amino acids. The body makes some of them. Some of them are essential amino acids, meaning you have to get them from diet. And very specifically, tyrosine and tryptophan are two amino acids that are not made by the human body. You have to get them from diet, and are critical in the production of some of the significant neurotransmitters like serotonin and norepinephrine and dopamine. Now, the reason I'm mentioning this is for two reasons. One is understanding how these molecules are made inside of the nerve cell, but the other thing too is that you can at times have an impact on mood dietarily. And we'll talk some about, we're going to be talking about adjunctive treatment, things you can do beyond medication treatment, and sometimes diet can have some impact on influencing certain symptoms, especially in mood disorders. The most striking example of the impact of a lack of adequate amino acids is in anorexia nervosa. And one of the reasons the drugs don't work very well, there are exceptions, but is because they're not even making enough of the neurotransmitters to have an impact on it. Okay, so the first stage of treating anorexia nervosa is, guess what? You get them to eat. Yeah, they've got to get some nutrients in there so they can actually use their brain. The blood-brain barrier is a great thing to have because it screens out lots and lots of toxins. In early primitive humans that were evolving in equatorial Africa, almost certainly they ate some plants that otherwise might be toxic, but many times didn't get into the nervous system because they were screened out by the blood-brain barrier. Now, the relevance of this is that drugs that are going to get into the brain, that need to get into the brain, have got to cross through the blood-brain barrier. And a lot of molecules can't. Or some of them can, but in just very small amounts, like the amino acid tryptophan, for instance, which is necessary for making melatonin and serotonin, does get into the brain, but not a lot. And so you can load up your circulatory system with tons of tryptophan, but only small amounts are going to get into the brain. So you have either it is an absolute barrier, or it partially screens out certain, especially larger molecules, but then some can go through into the brain very readily. And the ones that go right into the brain are fat-soluble, or sometimes called lipid-soluble molecules. And they just pass right through these membranes without any problem. And all the psychiatric drugs are able to do that. Okay. Now, again, just going over the basics, when there's a nerve impulse, there is the release of the neurotransmitter down at the end of the nerve cell, the terminal end, and it spills out the neurotransmitter into the synapse. There's a lot of details here I'm not going to go into, but one of them is that calcium plays a role here, that when the nerve impulse reaches the terminal end, one thing that it does is opens channels for calcium to come in, which facilitates ultimately the migration of the neurotransmitter down to the cell membrane and its release. And we're going to see in certain kinds of disorders there are problems with calcium. This is especially true with bipolar disorder. And in bipolar disorder, some drugs that are still considered to be experimental are calcium channel blockers. Okay, but just keep this in mind, that calcium plays a role really in turning on the nerve impulse to begin with, because back up in the cell body it's an important element that helps to facilitate activation of the nerve cell, but down here at the end of the synapse it plays a role also in the release of the neurotransmitter. The term ligands refer to molecules that bind to receptors, okay? And there are four primary types of ligands. Neurotransmitters, and the definition of a neurotransmitter is that it's a messenger molecule, okay? It carries a message from one nerve cell to the next, but it's in very close proximity. Okay, it's right next door, so it doesn't travel a long distance. Hormones, on the other hand, by definition, are travelers. They have a target. They're released into circulation, and they have a particular target. So, for instance, thyroid-stimulating hormone goes into the bloodstream and goes every place, but its target is the thyroid gland. Okay, and so the main difference then, or one of the main differences between neurotransmitter and hormone is hormones have an impact on more distant glands, okay, or nerve cells. An example of this might be that estrogen plays an important role in certain parts of the nervous system, and we're going to see later that there are changes in female reproductive cycles and hormonal changes that can have a profound effect in some women because the impact of estrogen, which is made in the body but reaches the brain as well. Okay, cytokines we'll only talk about very briefly. These are made by white blood cells, and the major component of the immune system. And there's a two-way communication between cytokines and the brain. The brain releases molecules that actually can bind to the cells of the immune system and influence that. Vice versa, cytokines can be released by the immune system and have an effect on the brain. And probably everybody knows numerous ways that emotional states and a person's use of their mind and so forth can have profound effects on overall physiology as well as the functioning of the immune system. Okay, and then drugs. Okay, so all of these are made inside the body, but these are foreign substances that act as ligands. So ligands, by definition, are things that will bind to and activate a receptor. Right? Ion gates, and this is a cartoon here of the membrane of a nerve cell, and ion gates are channels, and these are proteins, and proteins, when you stimulate them, they actually move. They change shape, at least momentarily, and so normally ion channels are closed, and then when they get activated, the protein bends for a fraction of a second, allowing certain things out here to enter into the fluid inside of the nerve cell. And ion channels are very specific. You open, for instance, a chloride ion channel, other molecules won't go in, but chloride will, okay? And that'll have an effect on the cell. Also, ion channels, when they're activated, respond immediately. So any drug that activates an ion channel is a drug that you can notice can have very fast responses. Now, in psychiatry, the two drugs that have very quick response are stimulants used to treat ADHD, and also the tranquilizers, and like Valium and Xanax and so forth. Now, if you take a tranquilizer, it'll take 45 minutes to get through your gut and liver and up into the brain. So, I mean, you can't pop a pill and immediately feel the difference. It takes a little while for it to get to the brain, but once it's there, it activates ion channels. Okay, and we'll get into the details of that later. Okay, most of the psychiatric drugs do not have a direct impact on ion channels. Okay, with the release of the neurotransmitter into the synapse, several things happen. Well, let's say that this is a norepinephrine nerve cell and spitting out norepinephrine molecules. With each nerve impulse, it's estimated there's a release of about 300,000 molecules. And how they figured that out, I don't have a clue, but maybe somebody just made that up. But anyway, there's a lot of this stuff that gets released. And then what happens to it, basically three things will happen. One is it'll bind to a receptor, a very specific receptor, stay there momentarily and then get knocked off, kicked off, okay? It'll have an effect on the receptor, that's one thing. The other thing is it'll get reabsorbed into the nerve cell and used again and again. This is reuptake, okay? The other thing is it gets destroyed by enzymes. And sometimes the enzymes are in here before they get packaged back up in these protective vesicles. They can be degraded by enzymes. The most important in psychiatry to understand is MAO, monoamine oxidase, okay, can destroy some of the neurotransmitter in here. But some of the third thing is, okay, they act on receptors, they get recirculated by way of reuptake. The third thing is that some of it leaks out into the surrounding fluid and eventually also gets degraded by enzymes. Now, the relevance of that is we'll look at a little bit of research where they have been able to measure levels of neurotransmitter action in the brain directly by looking at concentrations in spinal fluid. By the time these neurotransmitters get into spinal fluid, though, they have been degraded by enzymes. So you're not actually measuring the neurotransmitter, but you're measuring the byproduct, okay, the neurotransmitter metabolite. And this research is really not done really at all in the United States. But the research was done, some of the early research was done years ago. Since then it's been determined that, hey, this is too risky. You do a spinal tap, there's always some risk of damaging the spinal cord. And it's too risky, so it's just not worth the risk. But the other part of this is kind of the dark side of neuroscience research is that up until even recently, they'll go to really impoverished parts of the world like Eastern Europe. They'll find people who have a particular disorder like schizophrenia, for instance, and they'll say, we'll give you $100 if you let us do a spinal tap. And when that really amounts to about 4 months' salary for these very poor people, then they'll do it. It's basically taking advantage of people that are impoverished to get this data. So anyway, just keep in mind that has been one way of measuring the activity of neurotransmitters. Now there are new imaging techniques that are much safer, where they call it radio label, and they will get a particular molecule that will bind selectively, let's say, to serotonin receptors. And so you give a person an IV injection of this, let it get up in the brain, and then put them in a PET scanner, and then you'll see the serotonin system light up like a Christmas tree. That's not completely non-invasive because you are obviously injecting something into their body, but basically it's safe. And so there are new technologies that are safer. Okay. Okay, now receptors. There are different kinds of receptors. The ones that are the most important in psychiatry are receptors that are on the surface of nerve cells. Okay, so it could be on the cell body, could be on a dendrite, could be on, but most of them are on these dendritic spines, and these are manufactured inside of the nerve cell. And it's some nerve cells may in fact make 20 or 30 different classes of receptors. They may have dopamine receptors and acetylcholine receptors and GABA receptors and so on and so forth, which means that as it produces a variety of different kinds of neurotransmitters, it allows then that cell to be influenced by a variety of different chemicals. Okay, so even though you have, let's say, a serotonin nerve cell, it may have and secretes serotonin. It may have a dozen different types of receptors, though, that can potentially activate it. Everybody with me on that? Okay. All right. And these are made down in the nerve cell. They float up the surface of the internal surface of the cell membrane. Okay, and they weave in and out, and then they're operational. And these proteins are, by definition, are long chains, very specific chains of amino acids. And the point, and I know that my biology students know this by heart, but the point of my saying this is that once a receptor is up and working, it lasts about a day to a day and a half, 12 to 24 hours, and then it starts to kind of fall apart. It wears out. So what this means is that the cell has to continuously monitor the different types of receptors and more or less the absolute number of receptors on its cell. This varies a lot, but most nerve cells will have probably a total of maybe 3,000 receptors. And so the mechanisms for detecting the fact that I've lost, like 25 dopamine receptors or what have you, I don't think it's well understood, but cells can do this to an exquisite degree. And what they do, then if they detect, oops, we're down 25 dopamine receptors, it activates the dopamine receptor factory. It causes the production of replacement receptors that then get it back up to normal. And this is and maintaining the relative ratio and balance of receptors is going to have a lot to do with determining the baseline sensitivity of a nerve cell. Some of these receptors are excitatory, meaning when they get activated they turn on the cell. Some of them are inhibitory, which are like a braking mechanism. And so the overall sensitivity has to do then with sort of, in a sense, the ratio of an excitatory and inhibitory. Some psychiatric disorders, the number of receptors gets way out of whack, and that could be part of what's causing symptoms. Also, a number of the drugs ultimately will have an impact on hopefully normalizing populations of receptors. That's how a lot of these drugs work, is they just try to get the nerve cell back into a normal state of functioning. Okay. We're going to look at mostly postsynaptic receptors. We're going to say a lot of these drugs operate postsynaptically. What that means is you have a nerve cell, it shoots out a neurotransmitter, and it activates a receptor on the other side, the adjacent nerve cell. But in a few cases, we'll talk about drugs that have an effect on presynaptic receptors. So a lot of the literature you read focuses mainly on postsynaptic receptors, but there also are presynaptic receptors. Many times they're called autoreceptors. Once the nerve fires, then its own neurotransmitter comes back and shuts it off. There's like an inhibitory receptor on the presynaptic side. It gets turned on and it shuts it off. It's like the accelerator and the brake, accelerator and brake. Okay, so we can see them on either side of the synapse. Receptors can be described as being inhibitory, meaning they reduce the likelihood of a nerve cell firing. Excitatory, they turn them on. Ionic versus metabotropic, we'll talk about that in just a minute. And finally are intracellular receptors. And these are receptors not on the cell body, but they're floating around inside the nerve cell. And one example of this would be estrogen receptors are not on the surface of nerve cells, but they are in the fluid inside. And so estrogen penetrates through the cell membrane and binds with receptors inside. The target, though, really, for most of the psychiatric drugs are to have some impact on the postsynaptic receptors, but there are exceptions to that. And then finally, metabotropic receptors. Here we have this diagram shows an ionic receptor. It gets activated and in come ions that turn on the cell or may shut it down. Metabotropic receptors are the other kinds of postsynaptic receptors, and when they get activated, they don't directly cause the nerve cell to fire, but they set in motion a gradual change in the internal chemistry of these cells. And what happens, let's use the example of somebody who has acute onset severe depression in response to a horrible life event, like someone whose 2 children are killed in a car wreck. Now, obviously, there are going to be immediate symptoms, grief and sadness and a whole range of emotional symptoms. There may be early onset of some sleep disturbances, especially trouble going to sleep. But if this is beyond normal grief and it's really actually headed in the direction of major depression, typically a lot of the more severe vegetative symptoms like significant appetite loss, loss of libido, marked disruption of sleep, early morning awakening, typically don't happen suddenly. Okay, so you have the acute onset emotional reactions, but what happens over a period probably of weeks, and maybe longer than that, is if they slip into major depression, and this happens to 25% of people who have the loss of a loved one, okay? Probably what's happening is there is a gradual change in the internal chemistry of some of the nerve cells that regulate these biological functions, such as appetite and sex drive. In other words, the impact of the stressful event on changing this chemistry doesn't happen immediately so much as it happens relatively gradually over a period of weeks. And so then the nerve cell is functioning in an abnormal way. And the most adaptive thing that I could think of is if you have a horrible catastrophe like losing a child, you've got your plate is full in terms of just suffering. The last thing in the world you need now is sleep deprivation. You know, waking up 10 times during the night or waking up at 4:30 in the morning. People don't function well when they're deprived of sleep, and yet that's one of the complications of major depression is significant disruption of sleep. And that's pathology. There's nothing about that is in the direction of coping and resiliency. So the name of the game then is to by one means or another do something to normalize the internal chemistry so the cell works appropriately. And there are several ways to do this. One way that I don't have time to go into, but there are certain kinds of psychotherapy that can very significantly normalize functioning of certain brain circuits. And I think this has very, very clearly been demonstrated in the last 10 years. Okay? Now that's not a quick fix because oftentimes it takes 15 to 20 weeks of therapy and specific kinds of therapies, but that's a non-medical approach. Another good non-medical approach is exercise. Okay? In many people, increased amount of bright light exposure can facilitate normalizing. This is not just seasonal affective disorder. Most types of depression, if you have more intense bright light, it actually helps to more quickly address some of these symptoms. And then finally are drugs. Okay, and so the goal then is to, the details we'll get to later on, but the goal is to get this nerve cell back to normal functioning. You know, so the person can sleep and they have energy and that kind of stuff. They still are going to have, obviously, lots of emotional things to deal with, but at least they're not exhausted and they're not losing 2 pounds a week or something like that. And that just simply takes time. It sets in motion changes. And so it's commonly referred to as the first messenger is the neurotransmitter that's released from an adjacent nerve cell, just a tiny distance away from this receptor. It activates this, and that sets in motion second messengers, which are a whole range of molecules. Most of them are enzymes, but this is really the target here, is to try to normalize the function of second messengers. And unfortunately, that takes a long time. Oh, I left out one other thing that can very rapidly normalize second messengers and reduce symptoms, and that's ECT, shock therapy. Does it much faster than drugs. We'll in a later class we'll talk about ECT. We'll watch a video of ECT and see what that's all about. Okay. Now, just a couple more pieces here. Regulated systems. All biological systems in every organism share this in common. And what a regulated system is, it's that plants or animals have evolved to a place by way of natural selection that optimizes their ability to survive in a particular environment that they live in. But they have to have the capability to deal with stressors. So for a plant, it may be a prolonged drought, inadequate water, for instance. Okay. For animals, it may be being chased around too much by lions or something like that, and getting stressed out. And you can think of any number of ways that human beings get stressed out. So the physiology, the biology of the organism needs to be able to respond adaptively to increase the likelihood of surviving. Okay. But once the stressor's over, it needs to re-regulate itself and come back to a baseline, come back to homeostasis. Because staying in a stressed out state is dangerous ultimately, and so there are complex and really sophisticated mechanisms for all organ systems basically to respond to stressors, whether they are physical stressors or psychological stressors, but also certain brain structures and other ways of reestablishing homeostasis to bring them back to baseline. And we're going to see that there are a number of psychiatric disorders where there's a failure on the part of certain brain structures to do their job at getting the person back to homeostasis. Okay. And I want to talk about one concept here, because this is something that we'll see can be strongly influenced by psychiatric drugs, and it's up and down regulation. Okay, so let's say we're going to look at brain stress circuits later, especially when we talk about anxiety disorders. These very particular pathways. Now this is not a theory. This is a fact. Okay, very well mapped out in all kinds of animals, but we're going to focus on mammals, and obviously including human beings. And so let's say that these are two nerve cells. Here we have the terminal end of a nerve cell. Here we have maybe a spine on an adjacent nerve cell in this circuitry that underlies the fight or flight response. Okay, so if a person goes through a long period of time in their life where there's just low-level stresses, then every day this is going to get activated somewhat. It's activated right now. You feel tired, or your back hurts a little bit, or little low-level discomfort will cause a little activation. If you're driving home in heavy traffic, it'll obviously be jacked up a little bit more. But within relatively narrow parameters, okay? Huge stresses that occur abruptly can cause massive changes in body chemistry, like if you almost have a wreck, you know, that startle reaction that you have. But then that gets normalized very quickly and doesn't really change receptors. But exposure to very, very significant chronic stressors will make changes. So let's say that this is a person who has his wife has breast cancer and they're foreclosing on his house. Horrible, each one in itself, a really huge stressor. And so what's happened is maybe he's enjoyed many years of having normal life, no huge traumatic events, but now every day he wakes up, you know, and he's facing these things that are very significant. Okay, what's going to happen then is this stress system then is going to get activated chronically, and it's going to ramp up. It's going to be in higher gear, much more activation, much more release of neurotransmitters. And so one thing that occurs then is a cellular adaptation is over a period of probably over a period of a few days to a few weeks, is this nerve cell over here will make an adaptation. So it's not accustomed to getting bombarded by so much stuff. So what it'll do, remember these receptors are dying off every 12 or 24 hours. So at some point it just doesn't replace as many, okay? And so it's like, hey, you can smack me with as much norepinephrine as you want, but I'm not going to respond as much because I don't have as many receptors. So it's actually what it's done is reduce the sensitivity then over here, and this helps the person calm down. And when people habituate to stresses, this is a part of it, okay? I mean, there's other mechanisms as well, but with time there's some degree of biological adaptation, and this is referred to as down-regulation of receptors, okay? Everybody with me? Okay. Conversely is upregulation. And I use the example here of major depression, where let's say that there's a normal amount of neurotransmitter being released day in and day out, about the same amount. But then depression sets in, and we'll talk specifically about what depression does to nerve cells later. But what it does, I mean, one thing that it does is it reduces the availability of at least one or oftentimes several neurotransmitters, and like serotonin and dopamine, for instance, would be examples. So, in a sense, this circuitry here has become accustomed to a certain amount of activation every day, but now there's hardly any or very little neurotransmitter being released, maybe a little bit, but not a whole lot. And so first line of adaptation then is, okay, I've only got a few receptors here. I'm just going to repopulate this with more receptors. That way I have a better chance of catching more of these molecules when they get released in the synapse. And now it's attempting to normalize, okay? So once again, we will see that the notions of up and down regulation are important in understanding psychiatric medications. Okay. Neurotransmitters, and then just a few minutes from now we're going to take a break. Lock and key metaphor is very appropriate, and that is you get a ligand, okay, and it will bind to a receptor, and let's say that, but it's highly selective. So let's say that you have a dopamine receptor. And now there's a dopamine molecule, and it binds to that, and it activates it. Okay, so in a sense, that's the key goes in and unlocks the lock, and then the receptor does its job. Most of the time, it affects a metabotropic receptor, sometimes an ion channel. Okay, you have a serotonin molecule come along, it'll do nothing to that receptor because it's highly selective. Okay, so drugs or neurotransmitters or hormones that activate receptors and result in a greater likelihood of activating the nerve cell are called agonists. Okay. Now, the flip side of this are antagonists. Antagonists block receptors. And lock and key metaphor again is good. It's like if you have a deadbolt lock, your key will unlock it, okay? There are many other keys that will actually fit into the lock but won't unlock it. But when the other key that is not going to open the door is occupying the lock, then the other key can't get in. And this is what you see like with antipsychotic medications, where the drug binds to a receptor. And in most instances, it's a dopamine receptor. And it prevents dopamine then from normally activating that nerve cell. So that would be considered to be antagonist. Now, this gets a little complicated. Let's see if we can understand this. We're going to go through this and then we'll take a break. Okay. Now, let's say that, remember, receptors can either be excitatory or inhibitory, which means they either work in the direction of turning the cell on or they reduce the likelihood of the cell being turned on. Accelerator, brake kind of metaphor I think is okay. Now, one thing is you can have a drug, let's say any kind of ligand, it can be a neurotransmitter, drug, or what have you, that's an agonist, and it binds with a receptor that is excitatory, then it's going to work to turn the cell on. That's the plus sign. But let's say you have an agonist and it turns on an inhibitory receptor, what's the result? If it's a brake on. So the point I'm making is agonist, antagonist by themselves don't tell you exactly what happens until you look at what receptor it affects. Okay? Now, again, antagonist, you have an excitatory receptor, but it gets blocked by this. What's it going to do? It's going to reduce the likelihood of that cell turning on. Right? An antagonist that blocks an inhibitory receptor will temporarily disconnect the brake, and it'll be more likely that it'll turn the nerve cell on. Okay, everybody with me on that? Okay. I don't know, for me, when I first learned this, like, huh? No, wait a minute, let me look at that again. Okay. So that's going to be an important concept to keep in mind.